All right, problem 8, a little bit more complicated than problem 7, but still not too bad. In this case, we're measuring the concentration of the reactant, in this case, you can see it's diminishing, as a function of time, and the problem is to use that data to figure out the order of reaction and a number of other things. So, first question is, what's the order of the reaction and the value of the rate constant, and what are the units on the rate constant? Coming over to this side, there's a proper way to do this, and I didn't really do it that way. So what I did was, here's the time, here's the concentration. I just took differences between adjacent concentration values for the logarithm of p or for 1 over p. I'm assuming that the order is either first order or second order. If it's first order, then I should get a straight line, in which case these concentration differences should all be fairly similar and shouldn't show any trends like they do, in fact, in this case. Because if there's a trend, right, then the slope is changing, and that means you've got a curved line. For 1 over p, if it's a second order, right, that would be a 1 over a versus t plot. Then again, the differences between adjacent points should be more or less constant. And you can see in this case, they aren't really constant because I've put some artificial noise into this data now. It's not perfect data anymore. And so there's some noise in these differences too, but they don't have a trend. They're not going anywhere. This one's 3.8, this one's 4.4, that one's 4.1, and this one's 4.0. They're all hovering right around 4. Whereas in this case, it starts at 0.24 and ends at 0.14, and they're going systematically down. That looks like a curve to me. This looks like a straight line to me. So I conclude that it's second order. The way to really prove that would be to plot 1 over p here in this case, versus t, and show that you get a straight line. It should be a straight line with a positive slope. And then the slope of that would be the rate constant. And so the problem actually asks, what are the units of the rate constant? And so the units, since it's second order, the units on the rate constant should be molar to the -1, seconds to the -1. All right, the next part of the problem asks for, at long times, the concentrations converge on values of P for 0.05 millimolar, P2 of 0.05 millimolar, and we want to know what the standard molar Gibbs free energy of reaction in this case is, right? So we want delta G R standard state. How are we going to do that? Well, these are the equilibrium values, right? So we can calculate an equilibrium constant, and that's what I've done over here. I'm calculating the equilibrium constant by putting P2 over P squared for this particular reaction. 0.05 millimolar is 5 times 10 to the -5. Same for the P concentration, only that's squared, which gives an overall equilibrium constant of 2 times 10 to the -4. Remember the comments, though, that I said back in the main notes, and that is that if you put the units on this, millimolar or molar units on this, and also put the units on this, there'd be a molar in the numerator, a molar squared in the denominator, and that would seem to indicate that this number here has units of molar to the -1, whereas the equilibrium constant can't have units. And the problem is that these should really be activities, they should really be unitless, and that means this number really should be unitless also. And so what this molar to the -1 is really telling us is that this equilibrium constant is a Kc with a standard state of 1 molar concentration. That's the bottom line from this units business that comes up over and over again in all of kinetics and thermodynamics. All right, once we have the equilibrium constant, we can use our standard relationship to get the Gibbs free energy change for reaction. Our T is equal to 300 K in this case, I believe, yes. Log of k is log of 2 times 10 to the 4. So RT is 2494. That's our standard memorized number. And that gives, after the arithmetic, a delta G value of minus 24.7 kilojoules per mole. The next part of the problem asks for what the value of the reverse rate constant is. And to do that, we're going to use the principle can't spell, of detailed balance, which says, come back over, there we go, that the equilibrium constant is equal to the forward rate constant divided by the reverse rate constant for any elementary reaction, for any reversible elementary reaction. So I calculate the forward rate constant from a slope of this data, a slope of 1 over p versus t, and get a value of 2.03 times 2.03 molar to the minus 1 seconds to the minus 1. That gives me the K1 value that I need. Then K minus 1 is just K1 divided by the equilibrium constant, so that's 2.03 divided by 2 times 10 to the 4, which gives a reverse rate of 1.02 times 10 to the minus 4 seconds to the minus 1. One thing worth noticing, and I should have pointed this out earlier in the notes and didn't think of it, but the value of the rate constant is often, the equilibrium constant is often quite large, right? In this case, it's 2 times 10 to the 4, 20,000. That's also the ratio of the forward to the reverse rate constant. So if you see a pretty big equilibrium constant, and this is a fair to middling one, then you know that the reverse rate constant is a lot slower than the forward rate constant. Likewise, if you see something small, like 10 to the minus 5 or something, then you know that the backward rate is a lot faster than the forward rate, or anyway, the forward rate is a lot slower than the backward rate. And that's what we're seeing here, that the forward rate is only about 2. It's not very fast. The equilibrium constant's pretty high, and that means that the backward rate is really slow.